Hello, community. Today is the last day of 2024, and today is all about you, my viewers, my subscribers. And yesterday I showed you a video that we should ditch RAG for a better solution. And your comments were just beautiful. So you had here a great amount of comments. So let me reply to your comments. And I want to say I'm loving every one of it. So first one. Your pronunciation of RAG is horrible and I can't watch your videos for your horrible English. And you are absolutely right. I'm not an American. I'm not a native English speaking person. I'm here in the middle of Austria. And wherever you are positioned, North America, South America, Africa, Eurasia, Australia, you have your local community. And if you're an English speaking nation, your pronunciation is so much better than mine. So therefore, yes, you're right. I'm sure my pronunciation in English is simply horrible. But you know what? Then I just discovered, hey, wait a minute, because I record here, if you go here in your YouTube video to the audio tracks, you have an automatically dubbing here in 6 different languages by YouTube. This is not my voice. Only on one channel you hear my beautiful, clear, and gorgeous voice, and this is here original. Problem solved. Second one, your examples, especially in your last video here on RAG, clearly show that you have no idea about the real RAG. Don't you dare to make another video about RAG. And what I really liked was this one. Hey, your examples are so simple. They are just a joke and not the real complex real-world RAG. You know nothing about RAG. And you're right. In the past of my videos, I only provided here the theory or maybe the mathematical theory to this. And a lot of my viewers said, hey, can you provide us with some simple examples? So when we enter here a complete new topic, a complete new area of research, can you just show us on a simple example what we are talking about and not just start with the pure theory? So I started to search for simple examples. And I'm not good at this because the examples you find here in the scientific papers, they're real complex for some advanced audience. So I wanted to make it easier for you for a simple introduction to the topic. So I chosen here examples on my mind. They're all my examples that I try to make it as simple as possible. But you're right. Those examples don't show the full-fledged RAG version. And it never was intended to do so. And if you judge me on my short, simple, explanatory examples, I understand this. Absolutely correct. So, no problem with this. I get it what you want to tell me. Another one was interesting. It was plain and simple. I can't watch your videos for 20 minutes. Another one said, hey, only make videos of 1 to 2 minutes. Another one said, hey, don't explain key value cache. Because they said, hey, everybody knows everything about it. And I understand this. If you are an expert in your field and you work here with the different tensor algorithms every day, you don't want to see a simple explanation of the terms that I use in my video. But you know what? I make videos also for beginners, for persons that are not experts in their field. I want to show them new ideas. I'm fascinated by new topics. So I explain here the terms that I use and I provide simple examples. And I'm guilty as hell that I am this simple person, and you are right. And then there was a comment, hey, you have no videos in your video. And there was one that says, hey, you are on YouTube. So buy some stock video footage and show me videos like any other YouTube channel. And I get it. I understand what you want to tell me. I should invest more and show you when I talk about, a research in the lab. You want to see a video of a researcher on a YouTube stock footage that I buy, sitting here on the desk doing some research in the lab, because I understand. This is what everybody does. There's only a small problem. I don't feel like everybody else when I design my videos. What I really love was the comment, hey, don't explain anything, just the result. And I thought, I understand it here. But if I would do a video, so the procedure 12b gives us a result of a 24% increase and a factor beta, I think this would be quite a short video. And maybe it does not ignite the spark that you would say, hey, I find AI interesting. This is what I want to learn. Or maybe I want to try a new methodology. I want to try to follow here a complete new crazy idea. But I understand what you want to tell me. And then, you know what is really beautiful about this? And yeah, there was a comment, hey, you say beautiful in your videos, therefore it cannot be a science video because this is an emotion. And you are, again, absolutely right. This is not a science video at all. My videos should ignite a spark of excitement that you want to go and read the papers. You want to invest your time to find out something yourself about it. This is not a scientific video. Otherwise, it would go about 2-3 hours and we would go in every scientific detail. We would do mathematical proofs for every statement I do. But I don't want this. I want something else to achieve with this video. And the beautiful thing was nobody had any comment on the real method of cache augmented generation itself. They were all focusing here on me, on my mistakes. And I'm so sorry if I don't live up to your expectation. And there was one exception. Of course, there's always one exception to the rule. And somebody told me, hey, it will not work here for the closed proprietary O1 model from OpenAI. And again, you are right. What I told you here, you have access. If I talk about key value cache management, memory management, you have to have access to the model. And yes, you're right. They are closed proprietary models by OpenAI. They don't even show you the reasoning process of AI. They keep it secret. So there are models that some of my videos will not work. And starting some weeks ago, I told you I want to focus here on small large language model and vision language model that are open source, that are available, that we can download for all of us. I don't just want to focus here on these huge monolithic, extreme expensive corporate O1 or O3 models. I want that we can touch those models, work with those models. So great if you point out that there are some exceptions to the videos that I showed you where my method that I show you will not work. Great to point out the limitations of my video. And then I'm loving this. And then I have some people that have here, hey, who are you? You have a hidden agenda. What do you want to sell? Why you have no commercial ads? And you understand, for an American seeing a YouTube video, and I have no commercial ads, nobody is sponsoring me, I don't want to sell you a product. I don't have products that I want to sell you like merchandise or coffee cups or t-shirts. I don't want to do this. I want something else. And yes, and then the ultimate response that really touched my heart. Somebody accused me of this. You promote new knowledge. And I have to tell you, you got it. Yeah, absolutely. This is absolutely what I'm guilty of. I want, and I tell you this 2-3 times every video, read the papers, get fascinated, have an idea that there's another world out there. The AI research is extreme, 400, 800 papers per day. I can only show you maybe 1, 2, 5 papers per day. But there is a complexity out there you can explore. It's waiting for you. So, you are absolutely right. So this is it, just a short feedback. But now you also had other questions, and let's answer this and provide solutions to you. So you had another response, and this is not a topic. Now we start this video here on a little bit more scientific touch. You said, hey, I don't want to work with Gemini. I don't like it. I don't know what. It's too expensive, whatever. My models, my short context LLM, maximum 128K token length. This is a short context LLM, what we call it. And you ask me, hey, how can you find a solution that this CAG works only on my LLM? So, great response, and I hope I can provide a solution today how you can work with your short context LLM that only has a context length of 128K token length. you can also use it. It will not be a perfect solution, but it is a great improvement. And I discovered, designing this video, that this is also kind of a new approach, a new perspective, because you asked me, hey, in your video here, when you move from the large language model to the large concept model by meta, what is this concept that the model is now calculating? And I think with this explanation, this is also kind of explaining what is a concept here in Meta's LCM models. So let's start the video. In my last one, again, a reply, everybody was talking about here the size. The size of your context length is not as important if you really separate the data that you normally store in a vector store and you say, hey, all the individual financial data of all the persons have nothing to do in a vector store. We have to separate them in a secure database. Therefore, the size of the vector store reduces significantly because all the sensitive private information is gone. I wanted to indicate with this image that the vector store shrinks significantly and is now within the scope of handling with a CAG. I was not able to make this point, so let's try it this way. And then there was a response that says, hey, but I have only 128K, so I can only put this in, and this is it, and it is limited to this very short context length. Here at 19 minutes and 30 seconds, I said, hey, but is the maximum context length of your LLM, your 128K token LLM, a limiting factor? And at this very second, I showed you and I give you an answer. It is not a limiting factor. And the rest of the video, I explained to you why. But, well, those people that asked me, hey, this is here a limitation, never made it to minute 19. So let's find another solution. Let's have a look. So let's reformulate it a little bit more that we can handle it. So your question is how to improve the efficiency and the effectiveness of a short context LLM, max 128K token, when we want to tackle here some long-range reasoning tasks that go beyond the 128K if we have here an ICL prompt with all the bells and whistles. Is there a new methodology? And the answer is yes, it is out there. And since nobody of you knows about it, this is why I do this video. It's a 3-step process. Step 1, create a structured memory defined by typed hierarchy schema. Step 2, after processing now a short segmented piece here of a long prompt of this 2 million token prompt, now you segment it up in 5 or 10 pieces, whatever you need. Your short context LLM is prompted now to propose a revision to the structured memory we defined in schema 1 with the context now of this segment of information. And then step 3, this now leverages here the prefix key value caching. And you might say, hey, what a coincidence that in my last video you introduced here the key value cache. Yeah, it's absolute a coincidence, because the new memory is structured and revisions are incremental only. Remember in my last 2 videos where we were talking about continuous learning, continual learning process of our LLM? Now we are right on topic. This means that large portions of this external memory often remain unchanged between our processing step, and I will show you these processing steps. Yes, it will be an example. And we will intelligently, the memory management of the machine, reuse here the key value activation from previous steps from the unchanged part of the memory, avoiding here redundant computation. So we are faster, cheaper, and we hope to have a better performance. Why we are doing this? Because, and some viewers pointed this out, these long context models are computationally expensive due to the increased attention mechanism and whatever. We have a data scarcity. Training or fine-tuning those large LLMs with 2 million, 6 million token length, the data is not really there. So there are some synthetic training data. This is correct. And the model access, some of the powerful LLMs are proprietary. OpenAI 01, 03 model, absolutely correct. And many existing solutions for the long-range task are tailored to specific domains. So only work for particular tasks like a document summarization, and they lack here the generalizability that we want to achieve with our AI system. Okay, let's do this. So, the way we're gonna do this now to help you out of your misery that you only have a short context LLM of 128K is the form now of an externalized structured working memory for the LLM that enables now the LLM to effectively reason over information spanning far beyond their native context window. And we want to achieve this without fine-tuning the LLM or doing anything else. The only thing what we're going to use is in-context learning in an advanced form. And some of you are right, hey, the first was ECL, now the second was CAG. Now is there a new version in your third video? Welcome to my third video. What a coincidence. The main part, the most important element that you have to remember is here in this new method, the typed hierarchy schema. But this is nothing special, you know this. This schema now acts as a very specific blueprint for the external memory we're going to build together. And it is simple. I will have a simple example. Shocking. So it's a user-defined, or maybe I will show you how you write some code that the LLM can generate this, and especially helpful in my particular case for my domain was Gemini 2.0 thinking experimental. And we have an outlining of the specification. What we need as a minimum set, the data types, the basic data types to be stored, integer, string, boolean, the data structure, how the basic data types are organized into some more complex structure, hierarchically. We have Python list, dictionary, maps, whatever. And then the hierarchy itself, the nested structure and the relationship between the different data elements, often represented as nested key value maps. Think of it like, this JSON structure with some predefined types of each field. So you see, as simple as could be. What we start with? We start with a memory initialization. So the externalized, notice, we are not talking about modifying the tensor weight structure of the LLM. We have an external memory. Every agent has an external memory. Starts with an empty structure. We start with the initialization. So our memory one step, empty. But it has to conform to our defined schema for our particular task. Great. So now for the first chunk, or for every chunk, DI, our short context LLM receives now a prompt containing the following elements. The task instruction itself. We have a high-level goal in our query. Summarize this document, find the relevant function for a mathematical topic, or code in Python the following problem. Then we have a specific query, the specific question or task related to the current chunk, may be implicit or derived here from the task instruction. And we have a schema that we have to define. This is the most important part. We have to define the perfect, optimal fitting schema for the specific part. This is a human, or later a LLM, predefined structure of the memory. This is how we want our memory structures. This is how we want our memory to be built. And then we start. We have a current memory state for each step DI, MI, and the structured memory accumulates now from processing the previous chunks and the current chunk, the DI, the current segment of our long-range input. Of our 2 million token input, we go with D1, only from 0 to 100K token. Now, the next step is that our short LLM outputs now a proposed memory revision. We want to build a perfect external memory to help our small, short context LLM to do some long-term reasoning. So this revision structured representation of the changes that are needed to update the memory based on the information in the current chunk, D1, or DI. So the revision, or I, is now a tuple, or better, a set of tuples of the form path, operation, value. This is the simplest form. You can add more if you want. Be creative. P is the path. It specifies the address within the structured memory where the change should occur. And you know this, often expressed using a notation similar to JSON path. So you know this. Then the operation. This is as simple as can be. It indicates the type of the modification. Either you add something or you update something. So you create a new element at a specified path, or you modify an existing element at the specified path. You have to be absolutely careful in designing your memory. And then you have the value itself, the new value to be added or used to update the memory element. And this value must conform to the data type defined in the schema for the specified path. You might say, easy? I told you so. A dedicated revision function is now happening, a revised memory that programmatically applies the proposed revision Ri to the current memory state Mi, resulting, and you're not going to believe this, in an updated memory state Mi+1. This ensures that the memory remains consistent with the predefined schema, and the update is not performed by the LLM itself, but, and this is the beauty, by the deterministic process based on the LLM structured output. We don't need the complexity of an LLM. We have other methodologies. Think about the paper I showed you yesterday about the coprocessor that Google is applying for optimizing the key value cache. So after processing all these chunks D1 to Dn, the final memory state, n+1, contains now the accumulated knowledge relevant to the long-range task. So this short LLM is now prompted one last time after running through all this iteration with the final task instruction, tFinal, potentially a slightly modified instruction to generate the final answer based on the completed memory for the ICL, then the original query, the memory schema itself, and the final memory state. This is the most valuable element here. This is why we do it. We want to get a final memory state, highly dense information that has all the information of this 2 million token reduced to a much shorter sequence. So this short LLM then uses this information to produce the final answer, and you do not have to pay Gemini for a 2 million, 6 million, 8 million token context length. Now there's a beautiful second part, and yes, I use the word beautiful, so you know this is not a scientific talk, this is a motivational talk that you go and you read the scientific paper that I have not shown you yet because it is so simple. The cache optimization here of our key value tensors. This is exactly what we talked about yesterday. And this method builds about the insight on yesterday's video. So, they found a simple rule, and I can tell you it was the University of Oxford and Google DeepMind. By consistently placing now the structured memory, so your MI, before the current chunk, DI, in your in-context learning prompt, we can now create a stable prefix. And as the memory evolves now incrementally with every chunk DI, a significant part of this prefix remains the same between the processing steps, because we work incrementally. And this is the beauty of our type. So what we have now two possibilities. We already looked at this. So we have in-place updates or we have amendments. Let's have a look at the in-place updates. So whenever a single memory element is updated directly, the key value cache can be reused for all the tokens representing the memory up to the point of the first change. Great, computational effective. Tokens representing the modified elements and the subsequent parts of the memory need to be recomputed, but only them. Second part, the amendments. So instead of directly updating, the revision decides to add new entries or a new branch in the memory. Something new is happening, a new class, a new Python data class is emerging. So this strategy now maximizes the key value cache reuse, which is exactly what we want in this simple video, because the majority of the previously processed memory remains unchanged. Again, great. So only the tokens representing the newly added information need to be computed. Isn't this beautiful? However, of course, the more complex you will be, this might increase the overall external memory size of your agent. But who cares? This is here to make you interested in the topic that you find even better solution than the University of Oxford or Google DeepMind. Let me show you a simple schema. And now all the alarm bells are ringing. My goodness, this is a simple example. He doesn't understand anything. You are so correct. And therefore, I let it generate by Gemini 2.0 flash thinking experimental, and I was playing with it, and it produced here this simple schema defined by Python classes: the data class character, the data class event, and the data class book summary. If you want to have a summary of a book, this would be a first starting point. You just want to know all the characters in the book that appear, so you classify them. You want to know all the events that happen on a dark summer evening. Bob looked at the eyes of Alice, and Alice looked at the eyes of Bob, and you know exactly what is happening in this event. And then you have the summary, the list of all the events with all the different fields. So we define here our most simple schema that Gemini 2.0 could think of. And now we start with another simplification. And now I will not show you a 2 million token prompt, because I would have problems putting this on the screen. And then I will segment the 2 million token prompt into 3 segments or 10 segments, depending on the short context LLM that you use. But I will use a simplified demonstration, just to make sure that we are on the same page here. The whole book, the whole 2 million context length is now those 3 elements, and we separate this in 3 different chunks. So imagine you have the 2 million token length strength, and then this is here a context length of 100,000 tokens, and another 100,000 tokens, and another 100,000 tokens. Let's start with the initialization of the memory. It's an empty book summary object. M1 book summary, empty. You see here the content, events, nothing, characters, nothing, boring. Now we start to process the chunk 1, our D1. So this short context LLM is now prompted with an instruction, the query, the schema, and the current memory M1 and the chunk D1. Exactly like I showed you before, now we do a simple example. That is not a real world example. We have the task, the query, the schema, this is represented now, the memory, up until now 0, and the text. This is D1. Let's see this. We have now R1, the revision proposal is happening. So the short-term LLM, understanding the task and the schema, proposes now the following revision, expressed conceptually as a list of tuples. So we get now R1. We have here a beautiful JSON path where we have now what has happened. The first tuple proposes here adding a new character named patches to the characters dictionary. And the second tuple, you see here event, adds a new event to the event list with a specific description. It is as simple as can be, but only for this simplified schema. If you go for mathematics or physics, your schema will be much different depending on your task. The revised memory function applies now R1 to M1, our memory. So we go now for the second memory step, revised memory, a function of memory 1 and revision 1. Conceptual implementation, here you have it, and here you have the result. Next step, we just repeat everything we did for chunk 2. So what we have the task, summarize the key event and characters, we have the query. Now in the text, suddenly, D2, a small brown mouse was named Squeaky is happening. We have the schema defined. We have the memory, the representation of M2, and we have again the text. So what is happening now in the revision proposal R2, you get it. We introduce Squeaky, a small brown mouse, and the memory update M3, a function of called the revised memory of M2 and R2, is done. And now we have in the characters our 2 acting characters in this book description. And then we start all over again with chunk 3, D3. So you see, a simple iteration. But what it helps us with, if using now in-place updates, all those representations of M2 and M3 might share here a significant prefix, the character information, and the key value cache can now reuse the computation for this shared part. And this helps us a lot, because any changes in the event list would require new computation. But if you use amendments, the memory might be represented by appending now some new information. So the representation of M2 would be a prefix of M3, of course. This could lead to an even greater key-value cache reuse as additions are simply appended. So you see, we have not only defined here if you want a condensed information in a structured schema, but we also apply now a specific notation for our in-context learning prompts. And this is that we place the memory now first, and we use the optimization of the external key-value cache memory to swap in this to the working memory of our LLM. The success, as I told you, is so much dependent that you get the design of the structured memory right for your particular task. Some general remarks: it needs to be the memory informative, concise, and well structured, and whatever. But remember, this structured memory and how you build it is the most powerful tool for enabling here the short context LLM to tackle complex, long-range reasoning tasks throughout our in-context learning without fine-tuning. I give you here from the University of Oxford and from Google DeepMind here some other data classes here for different schemas. If you have a question and answer schema, you see here other schemas, get the idea. If you do something with code, here some beautiful examples in this original paper. And my hidden agenda of the video is to show you a solution. If you have only a 128K LLM with this methodology, published the day after Christmas, 25th of December 2024, by the University of Oxford and Google DeepMind. And another comment was, I do not praise the authors. So I want now especially to praise you, the authors of this paper here by Google DeepMind and by University of Oxford. They have come up here, they call this PRISM, and they have here this beautiful idea that I just showed you in a simplification. Have a look at this. This is exactly how it works. The result that they tell us is here: superior performance and baseline to task. We're using at least 4 times smaller context than the long context models. So we can compress it 4 times. You can make it more dense with our particular structure. But it is also more token efficient and it saves you money. And they found out by leveraging it in the best optimal way, the key value caches, it achieves up to a 54% cost reduction when compared to alternatives. You can halve your cost. You have 4 times content compression for your smaller 128K LLM. What a great way to help here using short context LLMs with long-range task, doing here an incremental reasoning with a structured external memory. I hope you found it informative. I hope I implemented all the good and helpful comments by my viewers. And I guess since it's December 31st, 2024, this was the last video for this year. I hope you enjoyed it. I hope you found it interesting. I hope I spark a little bit, a kind of a spark of a motivation in you. And it would be great to see you all next day.